Examples of polynomials are anything that looks like a number times x raised to a power. So if I had 3x squared plus 2x, this is a polynomial. Each of these is a monomial, and when I add them or subtract them, we label them as polynomials. Now it's also a polynomial potentially if I have more than one variable in the mix. So if I had something like 2x squared y plus 3xy squared plus y squared, this is also a polynomial. So it's okay that we have different variables in there. The only thing that we need to make it a polynomial is we have got addition and subtraction between some of those monomial terms. Again, I don't really care about the vocabulary so much, but you will see the vocabulary polynomials show up in books a lot. What I want to start off with is some examples of addition and subtraction with polynomials, and then we'll get into talking about multiplication. So my first example here, I'm looking at 5x squared plus x minus 2. And I'm putting that whole thing in parentheses. I know my video got blurry. We're going to give that camera a second. Cool. So I've got 5x squared plus x minus 2. And from that entire piece, I'm going to subtract off x squared plus 3x minus 7. I have to have the parentheses in this problem because of the subtraction. If we're going to add or subtract these polynomials, in this case, we're going to subtract. What this is saying is I'm taking this whole thing and subtracting this whole thing, which means I'm subtracting the x and I'm subtracting the 3x and I'm subtracting the negative 7x. So we have to have the parentheses there so that we make sure that we're distributing through the operator of subtraction. This piece, nothing's happening to it. I'm just going to copy it down. I've got 5x squared plus x minus 2. And then I'm going to distribute in this operator of subtraction. I'm going to subtract that x squared. I'm going to subtract the 3x, and I'm going to subtract the negative 7. Now, it's your choice how you deal with that subtracting negative 7. A lot of times, the quickest thing to do is say that when I have a minus and another minus, we're going to turn that into a plus. It's okay to write this out. It's also totally fine to go straight to a plus 7. When we're adding and subtracting polynomials, we didn't really do anything. All we did was distribute the minus sign through. So the instructions for the problems suck. And I'm sorry, but that's just what the instructions look like in math books. What they mean is make your subtraction and then combine like terms. So when we talk about like terms, that means this x squared guy, anything else with an x squared in it, that's what I'm going to put together. So I've got this 5x squared term subtracting an x squared. So together, that's going to give me 4x squared. And I'll move on to my next term and see if there are any terms that are like the next one. I've got a plus x. So then I'm looking for anything else that has an x raised to the first power. So here, my negative 3x is that next piece. So I've got a positive x minus 3x. It's going to give me negative 2x. And last, we got our numbers here. I've got the constant of negative 2. And then we're subtracting negative 7, which is the same thing as adding 7. And overall, that's given me negative 2 plus 7, so it's plus 5. Not super exciting, but this is the final answer we'd be aiming for if the instructions were to add or subtract. Okay. we're going to look at this and desensitize ourselves to fractions. I've actually made our lives pretty easy on the fractions. So the first thing that I want to say, I've got this whole polynomial added to this other polynomial, which means I don't need any of those parentheses. Distributing out the addition doesn't do anything to change any of the signs. So by the magic of the whiteboard, I'm just going to erase the parentheses. Saves me time from having to write it all over again. Then I'm going to do the same thing we did on the last problem, and I'm going to look to combine those similar or like terms. So I've got this 2/3 of x squared plus 4/3 of x squared. Trying to decide if I should take a detour into fractions and common denominators. Would anyone like me to take a quick detour into fractions and common denominators? Let's say that I've got, I don't know, let's go with a Nestle's Crunch bar. I don't remember, Nestle's Crunch bars have little squares on them, I think, or maybe rectangles. I don't really know. Just pretend I've got some chocolate bar here. Part of the reason that we need common denominators is to make sure that if you are trying to share if you're trying to share this chocolate bar with your friends, you got to make sure that we're talking about equal sized pieces. So here's my chocolate bar, and I'm going to say that it's broken up into these 8 rectangles. Well, let's say I had a couple chocolate bars sitting out here. This is really dumb, but that's okay. And one of them was shaped like this. And there's another piece floating around over here shaped like this. And I bet you all would say that if we wanted these two to have equal amounts of chocolate, I'd have to break one of those pieces off and give it to this other person, so that each of us have 3 pieces of that chocolate. But the only way that we can really compare these is knowing what our unit was. So for each of these, our unit is actually 1/8 of the original chocolate bar, or it's like one of these chocolate bar pieces. So this guy is 4 of those chocolate bar pieces, or 4/8. And this one is 2 of those chocolate bar pieces, or 2/8. But to compare their size, we want them broken up into pieces that are the same size. Same thing happens when we're talking about numbers. So if I have like 5/3 and 5/6, well, I read this as 5/3, meaning 5/3 of something. I took something and I broke it up into 3 pieces. This says I took the same thing and broke it up into 6 pieces. So even though it looks like I've got the same number of them, this one was smaller pieces, so I've got less stuff. So whenever we're trying to compare or add or subtract fractions, we've got to be talking about the same size piece. That's why we talk about needing common denominators. The way that we can get common denominators is essentially if this said that I had some unit of, I don't know, guess I'm in a chocolate bar kind of mood, but if I had some unit of chocolate bar, this says that I broke that chocolate bar came in 3 pieces. And I had 5 of those 3 pieces. So I had those 3 that made up a whole chocolate bar plus 2 more of these. But this one over here said that I'm taking that same size chocolate bar, but instead of breaking it up into 3 pieces, I broke it up into 6. So this one over here only has 5 of those 6 pieces. This 5/3 over here tells me that I've got 5 of these giant pieces. So if we're talking about fractions, that denominator tells us how big the piece is, and the numerator tells us how many of them there are. Well, I can't just go adding these pieces to these pieces. If I want to put all of this together, I kind of have to fill in that spot. If I wanted to add these 2 things together. So if I'm going to add these 2 piles of chocolate together, I'm going to have to take the ones over here and break them apart. So now I don't have 5/3. Now when I look at that, I've actually got 1, 2, that was that 10/6. Now I can take all of these chocolate bar pieces and add them to these other ones. Now I'm looking at 10/6 plus these 5/6, and it looks like I've got 15/6 of a chocolate bar. I'm going to take these 2 like terms, the 2/3 x squared plus the 4/3 x squared. And when I put those together, I'm just going to write them next to each other, but I've got 2/3 x squared and 4/3 of an x squared. We're talking about the same size pieces, so we can go and add those together already. I've got 2 of them over here and 4 of them over here. So together, I've got 6/3 of an x squared. And then we can do our fraction thing and say, well, 6/3 is 6 divided by 3. I'm looking at 2x squared. And we'll do the next part. So now next, what do we have? I've got my x's. So I've got -1/5 x and -4/5 x. Well, when I throw those together, and I'm just going to kind of keep that grouped. I'm only putting parentheses around it to visually separate it on the board. We don't actually need them there mathematically. So for our next piece, I've got the -1/5 x minus 4/5 x. I'm going to do the same thing. They're the same size pieces already, so we can already combine them together. Well, -1 minus 4, I'm going to end up with -5. -5/5 of an x. And if we wanted to simplify that more, -5 over +5 is going to be a -1. And I see a question in the chat, and I am headed your way. Okay. So when we're adding these fractions, it is true that the x squareds don't change. Part of that is like a visual notation thing, that when I have something like 2/3 x squared, this is equivalent to writing 2x squared over 3. These two are equivalent, even though one looks kind of different from the other. So when I'm adding the 2x squared, the 2/3 x squared, and the 4/3 x squared, I could also think about that as the size of my pieces are the same, so I know it's going to be over 3, but then I can kind of think about my numerator as saying 2x squared plus 4x squared. So together, that's going to look like 6x squared. And then I just remember the size of my pieces were 1/3. I don't know if that helped, but it'll probably get better as we do more examples. Our last part is me dropping a glass off the table. It just had water. It's all good. I'm looking at -3/4 and a +7/4. When I put those together, I've got the same size pieces because we've got those 1/4. And now -3 + 7. When I put those together, I'm looking at +4/4, or we can write that as a 1. So my final answer here looks like this. Okay, so this thing's gross. There's all kinds of stuff in there. It's definitely a polynomial because it is a finite sum, which just means that it's stopped somewhere. It's a finite sum or difference, meaning I'm adding and subtracting a bunch of monomial terms. Well, if I wanted to simplify this or add and subtract, I'm going to start by identifying what those similar or like terms are. Well, if I just take my first piece, this is for xy. When I'm looking for a like term, that's going to mean we're kind of going to ignore the number for a second and just look at what the variable piece is. So the variables are an x to an invisible 1 times y to an invisible 1. So anything else in the list that has an xy in it, that's what I want to group together. So this 5xy, that's the only other piece that is a like term. And if I put those two together, 4xy plus 5xy, I'll have 9 of those xy's. Next term over, I'm looking at -3y. Scanning. Okay, I've got a -12y. So those two terms I can put together because they can have different constants, but the variables are the same and raised to the same power. Throwing those together, -3, -12, so -15y. Next one on my list, I've got a 2. So I'm going to be looking for anything that's a number. Well, that -4 is a number and the 7 is also a number. I'm going to put all of those together. 2 minus 4, I'm at -2, plus 7, I'm now at +5. And dealt with that term, that term. The only thing I've got left is the y squared. There's no one for him to hang out with, so we're just going to write plus y squared. So I'm going to show you two of the most kind of traditional conventional ways for multiplying polynomials. The first we usually talk about as FOIL. And let me just really quickly give us the instruction that what we're going to do is multiply. You will hear people use FOIL as if it's a verb. And what this means is to multiply the first, the outer, the inner, and the last. My guess is you all have seen this. My guess is you would do it naturally. At this point, it's probably pretty ingrained, but I'm going to walk through it slowly. So I've got these two terms. By the way, FOIL, in terms of the acronym, first, outer, inner, last, really only works if you're multiplying two pieces together and they each have only two terms, because that's the only way that you have a first, right? A set of the first terms, a set of the outer terms, the inner terms, and the last terms. So FOIL only works if I've got specifically two pieces and they each have two pieces. So if I were writing this out, the way this works is I take the first two terms, so the 2x times x, which would give me 2x squared, and then the outer terms, so my outer terms would be 2x and -7 because they're on the outside. 2x -7, so that's -14x. inner. So I would take the 3 and the x, multiply those together, get a plus 3x, and the last terms. So now I am looking, what color have I not used? Green. Now I'm looking at the 3 and the 7, or sorry, 3 and -7 to get -21. Then I want to make sure to combine like terms. I'd have 2x squared minus 11x minus 21. FOIL is great, specifically if I have two terms with two pieces. But after that, it kind of fails. So even though we use FOIL as a verb when lots of people are talking about math, this specific thing, we actually do less than the next two things that I'm going to show. But we tend to call it all foiling. When we say FOIL it out, people usually just mean multiply the polynomials. Okay, I'm going to erase this to show you two other options. I didn't actually have a name for this next one, but honestly, I think it's what most people use. And then last fall, my class decided, someone in the class was like, oh, it's the rainbow method. So now I'm calling it the rainbow method. I won't take credit for that. Yesenia Garcia gets credit for naming this the rainbow method as far as I'm concerned, but rainbow method is like FOIL, but you just draw rainbows. So I'm going to take this 2x term and I'm going to draw rainbows to the second piece. So I'm going to take 2x and multiply by x to get 2x squared. I'm going to take the 2x and multiply it by -7. Again, I'm drawing another rainbow here. 2x times -7, I get -14x. Then for my next piece, I'm going to draw new rainbows. So I'm going to take that 3 and he's going to get rainbows to the x and a rainbow to the -7. Now, the nice thing about doing this rainbow method, it works even if my polynomials are bigger, because if I had more terms over here, I would just end up with more rainbows. We're still going to, when we're done, combine like terms to end up with 2x squared minus 11x minus 21. The last method I'm going to show you in terms of multiplying stuff out is often referred to as the box or the lattice method. You end up writing a little bit more. So if you are actually not fast with writing, this next method is a little bit more time consuming. But if you want to be methodical about the problem, it can be helpful just to keep everything super organized. So my last option here for the box method is that we draw a box. And my box is going to be, oh, actually box is probably a bad word. Box is a three-dimensional object. I think that's why they switched to calling it lattice. It's just lattice is not a word that people use every day. So this is a 2x2 lattice because I have two terms here by two terms here. So I'm going to write the terms together. I've got a 2x, a positive 3, an x, and a -7. And then for each of my squares or rectangles or pieces of the lattice here, I'm going to multiply the edges. The nice thing about this is there's a really direct connection to area. So if I wanted to find the area of this particular, I'm going to call it a square. Okay, I'm just like having this moment as a mathy person that square has a specific meaning. So really it's a rectangle because this side is 3 and this side is not 3. So I'm going with rectangle. So if I want the area of this rectangle, I'd have 3 by -7. A little weird, we don't really think of negative areas, but that's kind of how this method works. I wanted the area of this rectangle, it's 2x by x. So when I multiply those together, I get 2x squared. Area of this rectangle is 2x by -7. So I'd have -14x. Area of this rectangle, 3 by x, and I'd have 3x. And then when I go to write my answers down, I just want to make sure, again, to combine my like terms. And these two terms both have x's. So I'd end up with 2x squared minus 11x minus 21. I'm going to go ahead and use rainbow method. So I'm going to take my first term and rainbow it in. So x squared times 2x squared. Just a review from yesterday when we're talking about those exponents, because I'm going to have an x squared times another x squared, they've got the same base, so I'll add those exponents. So I'll have 2x to the 2 plus 2. Distributing to my next piece, I'm going to have minus 5x squared. And I'm going to go ahead and draw my other rainbows upside down just for cleanliness on the board. So 3 times 2x squared, that's a 6x squared. And then 3 times -5 would give me -15. Now I'm going to want to clean it up and combine the like terms. So here, when I clean it up, 2 plus 2 is giving me 4. I've got 2x to the 4th. -x squared plus 6x squared. I'm going to land with a positive x squared and then that -15. That's going to be my final answer on this. Pausing just for a second, keeping an eye on the chat, not seeing anything. Both the box method and the rainbow work, even if I've got more terms. I tend to go with the rainbow method more often just because it's less writing. So when I do this, I'm going to start with that first term, the 2x, and I'm going to draw in. And again, the only reason that personally I'm drawing anything in is because I need the visual cues to keep track of what I've already taken care of. If you don't need those visual cues, you can just write down the answer, and that's also totally fine. So 2x squared plus, 2x times x squared would give me 2x to the 1 plus 3. 2x times 8x would give me 16x to the 1 plus 1. And 2x times 9 would give me 18x. Or my guess is most of you probably would have skipped to just 2x. Oops, I cannot add today, apparently. It's because I wrote the wrong thing. Awesome. 2x cubed plus 16x squared plus 18x. When I'm doing this and I go to distribute in my next term, the 1 to the x squared and then the 8x and then the 9, as I do this, I'm going to go ahead and line the pieces up so that I've already got my like terms kind of collected together. So 1 times x squared, I'll go ahead and put my x squared right here so that it's in line with the x squared terms. And then 1 times 8x, I'm looking at 8x, and 1 times 9, I've got 9. So now if I put all that together, I've got 2x cubed plus 17x squared, 18 plus 8, that's going to be 26x plus 9. I look at this kind of by convention. I go left to right. So I'm going to multiply these two terms together and then multiply the result times x plus 5. I'm going to speed things up on this one. I'm not going to draw out my arrows. I'm just kind of going to point with my fingers. So I'm going to take that x term. When I distribute it in, x times x, I've got x squared. X times 4, 4x. Then I'll move on to my next term, 3 times x, that's a 3x. And 3 times 4, that's 12. We have a choice. We could just multiply this directly, or we could combine like terms on this first. I'm going to choose to combine like terms over here and make that x squared plus 7x plus 12 times x plus 5. To do this multiplication, I'll start with my first term, that x squared, and it needs to get distributed to the x and to the 5. So x squared times x is going to give me x cubed, x squared times 5, 5x. That next piece, 7x, 7x times x, I'll have 7x squared, 7x times 5, that's 35x. And my last term, the 12 times x is going to give me, I did something weird here.
It's supposed to be 35x.
Thank you. Thank you. So 12 times x is going to give me 12x, and then 12 times 5 is 60. If we combine like terms, I think I've made another mistake.
Is 5x supposed to be squared?
Yes, it is. I'm going to pause in case anyone was dutifully writing down what I was writing down instead of trying the problem for yourself. Just to make sure, did I make any other mistakes?
Could you do the pointing again? I feel like when we were writing, we weren't seeing where you were pointing.
I think I was trying to not draw in my little rainbows, and I'm going to go back to drawing them in. So if I'm looking at the x squared goes to x. That's my x cubed. X squared times 5, that's 5x squared. Then, because I can easily erase them, I will, to keep it a little cleaner. 7x times x, that's 7x squared. 7x times 5, that's 35x. And 12 times x, that's my 12x. 12 times 5, that's my 60. Upshot of all of that, even when you do a lot of math every day for many, many years, it's easy to make a mistake with the algebra. Having tools to go back through and methodically try to find your mistake, that's what's super helpful. Okay. I'm going to erase this. Oh no, we were going to combine like terms. Ooh, okay. Don't skip that step. So in terms of like terms, I've got an x cubed, and then I've got 2 of these x squared terms. So 5 plus 7 is going to give me 12x squared. So I'm looking at x cubed plus 12x squared. My x terms, 35 and 12 looks like 47x, and then plus 60. I'm going to walk through the algorithm that I learned when I was doing long division. We take the thing on top, the 461, and we're going to try to divide that into 11 pieces. And the way that the algorithm, the most standard Western algorithm works, is I look at this thing and I say, does 11 multiply by some positive whole number to get me to 4? No, 11 is already bigger than 4. So I move over and I scoop the second piece. And I look at this and I say, what whole number can I multiply 11 by to get as close to 46 as possible without going over? And 11 times 4 is going to get me to 44, and that's the best I can do. So I write a 4 up here on top. I take the 4 and multiply it by 11 to get 44, and then I subtract the 44 from the 46. 6 minus 4, I've got a 2. 4 minus 4, that's a 0. I look at that 2, and I bring down this 1. Then I repeat the process. I'm looking at that 11 and I'm saying, what can I multiply 11 by to get as close to 21 as possible without going over? And the answer is 1. 11 times 1 would give me 11, and then I would subtract this and end up with 10. Now, when you were first learning to do division, you might have written this as like the answer was 41 R10 or remainder 10. But the mathier way to write that remainder is to say that 461 over 11 is equivalent to 41 plus 10 over 11. Because I put my remainder on the top and I keep my denominator the same. I am not asking you to do this for numbers, but we are going to do it for polynomials. So I want to do a quick example of kind of how this works when we're dividing polynomials instead of numbers. So I'm going to start off the same way. I'm going to take whatever's on top and I'm going to put that inside my division bar. And I'm going to take whatever's on the bottom and put that outside of my division bar. When we're dividing polynomials, one of the things that feels a little bit differently from when we're talking about numbers is the piece that I'm dividing by, I'm really only going to focus on the term with the highest power of x or y or w or whatever our variable is. But I'm only going to focus on the term with the highest power. So I'm going to look at that x and I'm going to look at the x squared inside and ask myself, what can I multiply x by to get to x squared? And the answer is x. Now I'm going to take that x and multiply it by the entire divisor. I think that's the mathy word for the thing that goes out here. I'm going to multiply the x by the thing that goes out here. So I'm going to have x times x and get x squared, and x times -3 to have -3x. Next, just like we did with numbers, I'm going to subtract. The key here is I'm subtracting the entire piece. I choose to put parentheses in. Other options, I've heard the catchphrase, draw the line and flip the signs. That works too, because I'm subtracting it. So now I'm going to have x squared minus x squared, which would give me 0x squared, and -5x minus -3x. So -5 minus -3 will give me -2x. And just like we did with the numbers, once I've done the subtraction, I'm going to take that next term and bring it down. And repeat the whole process over again. So I've got that x out in front, and I'm comparing that to my -2x now, and thinking, what would I multiply x by to get -2x? The answer is -2. I'm going to take that -2 and multiply it by my entire term. So -2 times x would give me -2x. And -2 times -3 gives me +6. I'm going to subtract the whole thing. Well, -2x minus -2x, that's 0. And 8 minus 6 is 2. Once whatever is down here has a lower power of x than whatever is over here, we're done. So if you get to a number, you're definitely done. And if this were like an x squared and you got down to an x, you would also be done. So here, I'm going to say this whole fraction is equivalent to whatever's on top now, x minus 2 plus my remainder divided by x minus 3.